Hi, this is Mr. Wu, and welcome again to Disney Park Math. In episode 2, I'll talk a bit about G-Force, and again we'll feature the ride California Screamin'. Now, if you haven't watched the previous episode, definitely go ahead and do that first, where we talk about California Screamin' and talk about some basic principles here. So, California Screamin', just to refresh, is a classic theme roller coaster ride with some modern features such as a magnetic launch, an inversion, which is basically where the roller coaster goes upside down, a steel track, one of my favorite basic thrill rides, very smooth yet very thrilling. So to start, I want to talk about something I call the thrill formula. And this comes right out of physics and it applies to many thrill rides. And we call this F equals ma, which actually comes from Newton's second law of physics, very key formula, very key law there, which means this. Force is a product of mass and acceleration. Force equals mass times acceleration. And what this means, a couple of things. First of all, it's not really speed or velocity that makes a ride thrilling, but it's the force from acceleration, which is a change in velocity over time. A great illustration of this is when you're in a car on the freeway going at 65 miles per hour. If the speed doesn't change, you really don't feel anything. In fact, if you're a passenger, you could take a nap. What you feel is when that car stops suddenly, or if it's a high performance car, especially when it accelerates from a stop. You feel a force either in your back or your front. So then, velocity can also be changed in two different ways. Its magnitude, or its absolute value, which is its number value, like 65 miles per hour, and its direction. What direction is that velocity acting? Is it going forward, backwards, left, right, up, down, just different directions. So then, the greater the change in a ride's speed, magnitude, or direction over time, the greater the force or thrill. And we see that in a roller coaster ride. However, we can change the velocity, like in that magnetic launch, where we go from 0 to 55 miles per hour. We get changed in velocity when we go up a hill or down, when we go around a banked curve, when we go in an inversion. All those affect a change in the ride's speed, magnitude, or direction. Therefore, we feel a force, a thrill. Our body reacts. We sway back and forth, up and down. We push back on our seats, and so forth. So let's extend this. Let's talk now about g-forces. Even at rest, you're actually accelerating due to the Earth's rotation and gravity. Its velocity is actually changing. So we're not conscious of this because it's always there. So you feel a force called weight. So F is equal to force is equal to mass times acceleration. In this case, G is equal to what we call the gravitational constant. It's the rate of acceleration due to gravity, which is equal to 9.8 meters per second, or 32 feet per second, or we say second squared. And again, you feel this all the time, so it doesn't really feel like much because you're used to it. So the force you normally experience from your weight is called 1g. So right now you're probably experiencing 1g of force somewhere on your bottom if you're sitting down or in your feet. So the forces produced by a ride's acceleration can actually be measured in multiples of 1g. So a 2g force would be twice what you feel due to gravity. So let's get back to some problem solving. So we know that California Screamin' accelerates from about 0 to 55 miles per hour in 4 seconds. That's what makes that launch thrilling. So if 1 g of force is produced by an acceleration of 32 feet per second squared, which converts to about 22 miles per hour per second, it's a little easier to understand because we think of speed in miles per hour, which is due to gravity, about how many g's is produced in the direction of the launch. Is it 1g, 2g's, less than 1g? Let's find out. So again, a hint. Think again of using rates, ratios, and proportions to solve this. Because again, acceleration and a change of velocity is a type of rate. Go ahead and pause the video here and solve the problem, and we'll see what you get on the next slide. So, did you work out a possible solution? Hopefully. So let's see what this might look like. Again, think proportion, and this problem actually involves a couple different steps. First of all, so we know that in 55 miles per hour, the ride accelerates, okay, to that speed in 4 seconds. Now we're going to turn this into a rate, actually a unit rate, by dividing the top by the bottom. Okay, so we get 13.75 miles per hour per second. That's the acceleration. So, based on the previous slide, we know that 1 g of force is produced by an acceleration of 22 miles per hour per second, and our ride accelerates at 13.75 miles per hour per second. Well, how many g's is that? So here's our unknown. Again, we're just matching up the quantities in the same order. G's is to acceleration as G's is to acceleration. There's our proportion. We can solve by cross product. So 22 times x is equal to 1 times 13.75. So 22x equals 13.75. Divide both sides by 22. And we get x is equal to about 0.6 g's. So in conclusion, a force of about 0.6 g's is produced in the direction of the launch. In this case, we feel it in our back. So you think, well, 0.6 g's, that's not a lot. But again, remember, this is not the g-force we feel going up and down, because that's gravity. The launch we feel in a different direction, in a forward direction. So we feel it in our back. So it's a different direction, so it's unusual. We don't normally experience that, so that makes the ride thrilling. So how do we verify this? This is not the most totally scientific thing, but there is an app out there called X-Sensor, which actually allows you to use the accelerometer on the phone to measure g-forces. If I look at the screen here, we see that we have 3 different directions. We measure g-forces in the x, y, and z directions. Now if you think of graphing, it's sort of like that. So my x direction goes from left to right, horizontal. Our y represents our vertical, which is g-forces experienced up and down. That makes sense because notice the green line here. It's about 1g, negative 1g. That's your weight. Now the z, that is our axis that goes right through the page, right? So that one's harder to maybe see here in 2 dimensions. So that would be the g-force you feel during that launch. So I'm going to show you kind of what this looks like when I'm using it on this ride. It's a little bit crazy, but here it goes. It's very shaky. I'm trying to measure here. Craziness, I know. So, what this app does is it takes measurements of the different g-forces and the 3 different axes there, and I get data. And what it's able to do is import this data into an Excel spreadsheet, and then from there I'm actually able to graph it. So which is kind of cool. I can get an idea of what this looks like. Again, here are my 3 axes, my xg's, my y's, and my z's, which are all accelerations. We can see how much it changes over time, the different forces that we're feeling, and so you can definitely see why this ride is thrilling. A couple of notes here. It's quite shaky, and part of the reason being is that, well, I'm holding my phone here, so any vibration or movement causes what we call kind of noise, so it's sort of variation in the data. But for instance, let's look at the launch. We know that is in the pen here. In the z direction here. So let me just look at the purple lines here. From the beginning of time here, our first jump up here goes up to about positive 1g. We measured before that we've calculated was about 0.6. So that's somewhat reasonable. And we notice it changes here over time. We can find out whether we're experiencing forces from the side or from the top to bottom. but just kind of gives you a good picture. And again, not totally scientific, but a good ballpark. And we could definitely do some things to clean up the data a little bit more. Okay, so just having some fun with the data there.